Can this little thing solve the water crisis? No, not by itself, but it can help, and this video will tell you how. Hold it. What water crisis? Don't we have lots of water? It depends. Some places have more than enough, but many places in the world are already in crisis. How is that possible? We all know about the water cycle. Doesn't that mean that water gets recycled and used again and again? Yes, but only a small portion of this water is usable, and demand for the water we can use just keeps going up and up. This can't go on forever. When demand exceeds supply, we end up in a water crisis. So what can we do? Solving this problem has many parts, but one thing will help is if farmers use less water. And that's where this little thing can help. It's a remote moisture sensor. Farmers bury it in their fields. It tells them exactly when and where they need to water their crops. This cuts down on the amount of water they use on their farms. But how do these sensors work? The farmer has a device that sends out radio waves at many frequencies. Think of tuning a radio by hand. You move the dial up and down until you get the station tuned in. Similarly, the farmer tries radio frequencies until she has the one that makes the sensor emit a strong response. That strong response is called resonance, and the radio wave frequency that caused it is called the resonant frequency. Let's go a bit deeper into what resonance is. Watch this woman. She raised the frequency of her voice until she found the right note to break the glass. Every object is made of molecules that naturally vibrate at a certain frequency. When the singer sings at exactly that frequency, the vibrations in the glass get stronger and stronger. Eventually, it vibrates so strongly that the glass shatters. This is an example of acoustic resonance. And the note that broke the glass? You guessed it. It's called the resonant frequency. What if the singer put water in the glass? Would this change the resonant frequency? Let's see.
And if I make the speed at which vibrations travel through it's forced into vibration, it will begin to vibrate at its natural frequency.
We can see that the more water there is in the glass, the lower its resonant frequency. Our little water sensors are similar. The wetter they are, the lower their resonant frequency. So are farmers singing to the water sensors to find out how wet the soil is? No. Our sensors are not acoustic sensors. They don't resonate in response to sound. They are electrical circuits, and they resonate in response to radio waves. Let's look again at our water sensor. The circuit is printed on cardstock paper. This paper absorbs water and becomes as wet as the soil that surrounds it. Do you notice this part of the circuit that looks like a bunch of parallel lines? This part is called the capacitor. The job of the capacitor is to store electricity. The wetter the cardstock gets, the more electricity the capacitor can store. And as the capacitor stores more electricity, the resonant frequency of the circuit gets lower. Let's imagine our farmer in her field. She tunes her radio wave emitter, trying lots of frequencies. She finds the frequency that makes the current in the sensor spike up. That tells her how much electricity the sensor's capacitor is storing, and thus how wet the paper is, and thus how wet the soil is. And presto, she knows if her crops need water. These sensors are not perfect. Right now, their big problem is that they only work at very short ranges. If the farmer's radio wave emitter is more than 10 centimeters from the circuit, it cannot be detected. 10 centimeters is enough depth to detect soil moisture for row crops, but not for trees, whose roots are much deeper. But they also have big advantages. They're cheap, mostly biodegradable, they can last for months, and we can expect improvements in design that will extend their range. Because they're so cheap, we can put huge numbers of them in the ground. Little robots would then roll up and down the rows of the field, reading the sensors. Of all the water in the world, only 3% is not salty. Farmers use 70% of this usable water. The researchers at IoT4Ag hope to reduce this number using technologies like our little water sensor. The less water farmers use, the more there is for everyone else, and the less likely we are to run out.